following Morris program. So remember, my setup, it's always X is a threefold. F, it's a foliation with non-decritical singularities. Of rank 2 on X. In other words, co-rank 1. And usually F delta it's a pair. Okay, so what we're going to do is exactly the same as what we did yesterday, following Morris program, namely, if Kf plus delta is an F, then there is nothing to do. We reached the Mia model, we didn't have to do anything. So we are happy. Okay, so we are going to assume that it is not an F. So exactly like in Morris program, also I should say that although I never talk about this, and I'm not going to do it, the cone theorem holds if F admits canonical singularity. And this is due to spicing. Okay, although I never talk about cone theorem, I mean, I never say what is the statement, and I'm not going to do it, but what this implies is that there exists, exactly like in Morris program, are extreme array, meaning that it's array given by, generated by some class C up to numerical equivalence, such that Kf plus delta is negative. So if you look at the cone of curves, the cone of curves looks around the point C, it looks like this. Okay, so it's the unique ray, I mean, we can assume this unique ray for which Kf plus delta plus some ample, it's equal to 0. Okay, so in other words, let me write it. So there exists A ample. Sorry? Yeah, exactly, yes. It's exactly like the cone theorem. Yeah. And it's a curve, which is not obvious, but it's a curve, yeah. So there exists A such that Kf plus delta plus A times C is equal to 0, sorry, A example, such that this is equal to 0 if and only if C is in R. Okay, so we want to distinguish three cases. We define the locus of R to be the union of all such C. Of course, this is a subset of X. Okay, to say that Kf plus delta is set effective, it's pretty much equivalent to say that this locus is different, is proper. I mean, it's not equal to X. On the other hand, it's not even clear that it's closed, although this is quite easy. But one of the results by Spicer is that this is really a Zariski's closed subset. So since it contains at least one curve, C is contained in, of course, maybe I should say here. Of course, C is contained here. So it's always empty. Sorry, it's never empty. Because we're assuming that R is generated by one curve C. There are two cases. It's either a curve or a surface. Okay, so let's talk about this case first, although I'm not going to say much. The proofs here, modulo what we said yesterday, the proofs here are quite straightforward and quite classic as well. So what Spicer's proof is that in this case, so this is the first case, sorry. There exists a divisorial contraction which in particular is birational, and such that, let me call it phi, the exceptional locus of phi is exactly the locus of R. So it's a surface. Okay, which is exactly what we had yesterday. I mean, in one of the cases of the Mia model program. So it's possible, and it's not hard to check, that the singularities of Y are well behaved. I need to wait until it dries. So what we do in this case, exactly like yesterday, we may replace X with Y, and the induced foliation will replace the original foliation. Okay, so in this case, replace X by Y. And of course, whichever foliation you have on Y, which is induced by X, will be exactly what will be replaced. And same thing for delta. Okay, so, and this step, exactly like yesterday, can only happen finitely many times. For purely topological reason. Namely, B2 of X, it's always greater than B2 of Y. Okay, so if we live in a world where there are only divisorial contraction, or in other words, the locus, it's always a surface, then we're done. There is nothing more to prove. We can contract it, and we can only do it finitely many times. The problem is that this is not true, even for foliations. So we need to assume that it's possible the locus of R is a curve. You can think of it to be C. Of course, there could be more than one curve, but pretty much this is the only interesting curve. So what do we do? So again, Spicer can prove that there exists a contraction, but the goal would be to flip it. But the contraction that Spicer finds, such that, first of all, exactly like you expect, the exceptional locus of phi, it's equal to R. But for now, Y, it's an algebraic space. Okay, because the way he proves this theorem is by using a theorem by Artin, where he shows that something can be contracted. Okay, so this is nice, but it's not good enough, except for one case. So this is the last theorem I'm going to talk about of Spicer's thesis. which is if F is a smooth foliation, then first of all, there exists so only case 2 can occur. Sorry, only case 1 can occur. And moreover, the induced foliation on Y, it's also smooth. Okay, so this means that minimum of the program holds. Why? Because you have only divisorial contraction only finitely many, and you always stay in the smooth category. So in this case, we can find minimum model. What is the problem? The problem is that the condition of this theorem is way too strong. It's not like talking about smooth varieties. I mean, foliation almost always, well, not almost, but anyway, many cases they have singularities. So although this is a nice result, it's not enough. Okay, so from now on, I'm going to talk about what is new. Yep.
In general, is the property of foliation being canonical and non-critical preserved?
Yes. Actually, this is going to be very important. Both being canonical, maybe I should write it. I will use it later on. But being canonical. On the other hand, canonical is not good enough. But being canonical, maybe I'll write it here. Canonical and non-decritical is preserved under divisorial conduction. So it's the good category, although it's not good enough to prove theorem. If you want to now, we'll see it. We need to change category slightly. As usual, if you want to prove theorems, you need to work with delta. If you want to work with delta, canonical is not good. Okay, so canonical, non-decritical is good, but canonical is not the right category. KLT we saw yesterday that is also not the category, so we need to change, and log canonical is way too big. So we need to change category again. Okay, so let me talk about new results. And everything I'm going to talk about, it's a joint work with Spicer. So what I'm going to do is to mention the results, and then, time permitting, I will talk about them. So the first result is that flip exists. I should say that it's in a more general context, but let me leave it like this for a moment. So the second theorem is that many of you maybe already heard this expression. I will talk about it in a few minutes. Special termination holds. So you see, for flips, we don't have something as nice as this. So to show that flips terminate is by far more difficult. So we are not able to prove termination, but we're able to prove something which is good enough to prove the third theorem, which is the minimum of the program with scaling, as in BCHM, holds. So what it means is that instead of using Morris program, we use a slightly different version, and in many cases we are still able to find a minimum model. Okay, then the fourth theorem, which is strange because usually it's proven before one proves existence of flips. But the base point fit theorem also holds. And what is strange about this is that yesterday I told you that if Kf is bigger than F, then it's not necessarily semi-ample. So we need to be careful when we state this theorem. Okay, is there something which is not wet? Oh well. Okay, so I'm going to talk about this result, and then I will show some applications outside the minimum of the program. Okay, so as I announced before, and this is, I'm sorry about this, I need to be a little bit technical, although it's very simple, but I need to change category. So if you remember, we had canonical singularities, then we had KLT, and canonical does not imply KLT, and log canonical. Now, log canonical, exactly like in the minimum of the program, are way too wide. We cannot work with log canonical. Okay, there are many properties that are not true for log canonical. Canonical is not good for pairs. And KLT does not imply canonical. So it's also not good. So we need to introduce a fourth set of singularities, which for some of you it's already very familiar. It's DLT. So F delta is F DLT, and the reason why we call it F DLT because it's not quite DLT, but it's a slightly different version. If, first of all, the coefficient of delta are within 0 and 1, one included, and none of the SI is invariant. Okay, these are easy property of curves. But the most important property is that there exists a log resolution, exactly like yesterday, such that, okay, let me write it first. A of EI F delta is greater than epsilon EI for all EI exceptional. Okay, why is this not the same as KLT? It's not the same as KLT because I allow the coefficient of delta to be equal to 1, which is not true for KLT. Why is not the same as log canonical? Because I'm forcing to be greater, not greater or equal than epsilon EI. Sorry, minus epsilon EI, if you remember the definition of minus. Okay, so it's really in the middle between KLT and log canonical. Exactly like in the standard MMP. Okay, why are these good singularity? Well, exactly like before, FDT is preserved by MMP. Now we can work with pairs, and whatever step you take of the MMP, this property is preserved. Okay, now I need to define what a log canonical center is. Sorry about that. So, many of you probably already heard this word in the classical minimum of the program. If you have a subvariety W of X, this is called log canonical center. if there exists some G from Z to X, birational, and E exception divisor, prime exception divisor, such that, first of all, the equality holds. Okay, I'm going to comment on this in 1 minute. And the second property is that, so far I never talk about W, the center of E in X is W. So it looks like I'm contradicting myself, because here there is an equal, and here there is a strict inequality. But you see, DLT property, it just says that there is one log resolution, such that for all the exceptional guys, it's greater. But for sure there will be others, exception divisor, for which this is greater or equal, not greater. Okay, exactly like in the DLT world. Okay, so this object, we're going to see some example, really exists. And if you read about minimal the program, you'll find this word very, very frequently. So what we are doing is exactly the same here. But there are some differences. And some similarity. Okay, let's see, what are the differences? No, sorry, let me start from something similar. So this is exactly like in the world of Brashian geometry. What we prove is that if F delta is DLT, and W is a log canonical center, then F delta is log smooth at the generic point of W. So if you remember, this is not strange. We saw an example when I showed that smooth, that KLT is not a good condition. When I show that there could be some divisors which have log discrepancy equal to 0 and they're invariant, so in other words here there is equality, even in the case of a surface. Okay, so this is some kind of generalization of that example. Okay, so this is exactly like in the Brashian geometry world. On the other hand, this is exactly the opposite. So this example shows that there could be infinitely many. And this is a bit of a problem, but we can handle it. Infinitely many log canonical centers. I'm going to show a very simple example. So this does not happen in Brashian geometry. Log canonical centers are always finitely many. So let me show an example for foliation. So let's suppose that we have a pair which is log smooth. Where these are prime divisors, which are of course two surfaces. And of course, if you remember, they cannot be invariant. So they are not invariant. So this is D1, and this is D2. And I'm going to call C the intersection of these two surfaces. I'm assuming that this C is not empty. Okay, so C is equal to D1 intersect D2. Then it's very easy to show that C, it's a local canonical center. And this is exactly like in variation geometry. If you take a threefold, you take two surfaces that meet in one curve. If you blow up this curve, the low discrepancy will be 0. The discrepancy will be -1. So it's a local canonical center. Okay? So there is nothing new here. But, and this is different, for any P in C, this is also a local canonical center. Okay, so this is the first example. The second example, it's even easier. Okay, so let me show the example. So as a fact, and this follows from the definition, if S is invariant divisor, then automatically S is a local canonical center. This looks, I mean, this follows just from the definition, looks like something trivial, but it creates some problems. Why? Because let's assume that we have a fibration to a curve. So if you want, this is a smooth fibration, sorry, not smooth fibration, a fibration into a smooth curve. And let's suppose that F is the foliation induced. And also, let's assume that delta is equal to 0. Okay, then in this case, you have as many as invariant divisor as you want. Then any fiber, any smooth fiber, it's a local canonical center. Okay, so this shows that there could be infinitely many local canonical centers. Both this example and this example shows that there could be infinitely local canonical centers, which again never happens in variation geometry. But it's okay. Okay, so now I'm going to skip flip exists. Let me just state the theorem, but I'm not going to talk about them. Actually, let me skip all the proofs. I will talk a bit at the end if I have time. But let me state some results. Let me go back to the main theorems. Okay, so the first theorem was saying that flip exists. So there is not much to talk about, but let me say it in a more general setup. So let's suppose the setup is like before, namely we are on a threefold. F is a foliation of rank 2. It's non-decritical, although this is completely useless, but we'll see it in a few minutes. And F delta, it's a FDLT pair. Okay, so let's suppose that R, it's an extreme array. Which is KF plus delta negative. And let's suppose also, so this is more general than Spicer's theorem because we are talking about DLT. Oh, I should have said, sorry. Let me just say it without writing down. Oh, sorry, let me just say as a remark here. What we do at the very beginning is to reprove all the theorems by Spicer in this generality, but this is easy, to be honest, in this category. In other words, FDLT. So the Kohn theorem is true. Anything that I said before is true. Okay? So let's suppose that R is an extreme array, which is XPF plus delta negative, and assume that the locus of R is a curve. Then, this is really the contraction of R. It's really a proper morphism into a projective variety. This is not anymore an algebraic space, but it's a variety. But more importantly, the flip exists, which, remember, means that you have a diagram where whatever was negative here becomes positive here. Okay, so this is the first result. Now, the second result is what I call special termination. This is, in the case of Brashen geometries, due to Sokurov. I mean, it's, for foliation, it's our result, but in the classic MMP, this is a famous result by Sokurov. So what does it say? So as I said, we have no idea how many flips there are. If there are finitely many flips, then there is nothing to do. Okay? So let's suppose that F delta is below, as in theorem 1. And let's suppose that we have an infinite sequence of flips. This shouldn't exist, but since we don't know, let's suppose that this is true. Okay, so we are not able to find a contradiction again. We're not able to prove termination, but we prove a special termination. Namely, then, after finitely many steps, after many flips, the flipping locus, and I will explain what it means. The flipping locus and the flopping locus, sorry, and the flipped locus are disjoint from any low-canonical center. Okay, what is a flipping locus and flipped locus? So I'm going to call this phi, exactly like we did before, and this phi plus. The flipping locus is the exceptional locus of phi, which is not a divisor. By definition, this is small, so it's always a curve. And same story here. This is also never a divisor. This is the exceptional locus of phi plus. Okay, so you have, by definition, you have a lot of diagrams like this here. And we are not able to contradict the existence of infinitely many flips, but we are able to show that at least we're able to avoid low-canonical centers, which is good enough to prove theorems. So even in the case where there are infinitely many low-canonical centers. So of course, in this case, since the low-canonical centers cover everything, then it means that flips must terminate. Okay, because all the low-canonical centers cover the variety X. Okay, the third theorem It's exactly like in BCHM. Namely, minimum of the program with scaling holds. So maybe I should say some names. Here we are somehow generalizing a theorem by Shakurov, and here we are generalizing the main result of BCHM. So let me say what is the setup. So let's suppose, this is exactly like in BCHM. Let's suppose that F delta is like before, but as in BCHM, we need to assume that delta is big. Namely, it's of the form A plus B. So this is DLT pair, where A is ample, and B is greater or equal than 0. So I will talk about this a bit later. But if any big divisor can be written as A plus B, where A is ample and B is effective. So you should think of delta to be big. But I will talk about this later. It's a bit more delicate. So let's assume that there exists a device. Oh, let me use the notation I was using the first day. Let's assume that there exists that H0 of M kf plus delta is non-zero for some M. So the nice assumption would be that it's set effective. But we need to, in order to prove this theorem, we need to assume that it's actually Q effective. Then, there exists a contraction X to Y, rational, such that if F prime is the foliation of Y, and so let me call it psi, and delta prime is equal to psi star of delta, then kf prime plus delta prime is F. So in other words, we reach the end point. Remember, we had the big graph where we start from F delta. We don't know that F delta satisfies this property. We don't know that flips terminate. Okay, so there could be very possible that there are infinitely many paths going somewhere. Okay, where this never stops. But special termination tell us that there is one path which is good enough. So it's a finitely many number of steps where this is F prime delta prime is the end point. Okay? So the difference between termination and special termination is that termination tells us no matter what path you choose, you always get into an end point. It could be more than one end point, but you always get to stop. Special termination tells us, well, you need to choose the way more carefully. You need to go on a special route, and then you'll find your way. You'll find the end point. Okay? So this is the difference between special termination and termination. Any questions so far? Okay, so let me talk about Theorem 4, which for me was the most surprising one, and I will explain why. So let's suppose that the setup, so this is the placement free theorem. So it's the setup as above, namely threefold, foliation of rank 2, non-decritical, and so on. And let's suppose that F delta is exactly like in minimum of the program scaling of the form A plus B, where, so this is DLT, where A is sample and B is effective. So I'm assuming that I reach the endpoint. So in other words, I'm assuming that Kf plus delta is an F. Okay, then in this case, abundance should be true, and indeed it's true. Then Kf plus delta is semi-ample. Okay, so why is this strange? The reason is because, and we really thought there was some problem, but then we realized there's no problem. Even in the case of surfaces, in dimension 2, of course also in dimension 3, there exists F foliation of rank 1, such that, so needless to say that all these theorems are true also for surfaces, such that Kf is bigger than F, but Kf is not semi-ample. But you see, if you define, in the minimum of the program, what we always do, I mean, how do we show that Kx is, so if Kx is bigger than F, then Kx is semi-ample by using a theorem like this? So the way to do it is that Kf, being big, it's equivalent to, so maybe let me say mkx, it's equivalent to A plus B, where this is ample, this is by Kodaira theorem, Kodaira lemma. Okay, so I can define delta to be equal to epsilon A plus B, where epsilon is small enough. Okay? And also what I can do is to study Kf plus delta. So this is equal to, let's see, 1 plus epsilon m. I mean, at least it's numerically trivial, well, Q equivalent to 1 plus epsilon m times Kf, sorry. Did I get it right? Probably not. Yeah. Because delta is equal to epsilon A plus B, and A plus B is equal to mkf. So epsilon m comes from this times this. Okay, so clearly this is big enough. So clearly it looks like I can apply this theorem, and I can show that it's semi-ample. But why I cannot apply this theorem? The reason is because no matter how small epsilon is, this is not going to be FDLT. And why is that? This is very different from the minimum of the program in general, in the absolute case. The reason is because most likely, actually for sure, B will have components which are invariant in its support. So this is a bit technical, but I just want to show why you cannot apply standard tricks in this case. Might not be FDLT, simply because the first property fails, because some components of B might be invariant. And this is exactly what happened in this example. You should see A for sure is not invariant. Why? Because A is ample, so you can move A. There is not going to be, it's not going to be difficult to find an A which is not invariant. But B, you cannot move it. Usually you have very few choices for B. And so B most likely will have components which are invariant. So you cannot apply this theorem. Okay, so there is no contradiction. So in some sense, this is the best one can hope for in terms of abundance. Okay, So, let me give an idea how to prove this theorem. So it's strange because we prove it in a different way than what we usually do in the Bayesian geometry. The way we prove it is that we use flipping contraction, divisory contraction, to reduce, we proceed by induction of the Pekan number. So after finitely many steps, the Pekan number must stop to drop. So at this point, we must have reached an ample model. So this is the idea. We use the flipping theorem in order to prove the base point free theorem. Okay, so instead of giving you, before I give you some proof, I would like to show you some applications of this stuff. So, the first one, so maybe let me start from the last one, sorry. So it's completely independent from minimum of the program. Namely, if F is canonical, or F delta is F DLT, then, if one of these property holds, then F only admits non-decritical singularity. So this theorem is very strange, because the way we prove all these theorems was to assume that F is both DLT, F delta is F DLT, and non-decritical. But then we proved that assuming non-decriticality is totally useless, because it follows from these two properties, one of these two properties. So how to possibly prove one theorem like this if all the theorem require non-decriticality as assumption? So the idea of the proof is very simple. So we first take a log resolution. So this means that we take, remember, y delta y plus the exception locus of pi is log smooth. And the induced foliation, Fy, is simple, has simple singularities. There was one more assumption, but I'm not going to use it, so I'm going to just leave it like this. Okay? So we know that there exists such a log resolution. Okay? So now, simple implies non-decritical. Although it's not obvious, it's just done by hands. Because I gave the local description of simple. So it can just be checked that, so by local computation, simple implies non-decritical. Decritical, sorry. Decritical. Okay, so in particular, Fy is non-decritical. Okay, so the picture was we had X, and then we have Y. And now, on Y, on X I cannot apply MMP. Why? Because we don't know if it's non-decritical. We try to prove that it's non-decritical. And all our theorems requires that the foliation is non-decritical. But on Y we can apply the MMP. And we can apply an MMP that goes back to X. This is a bit of a cheat, but somehow this is the idea. So we can factor pi into steps of the KFY plus, how did I call it? This one, let me call it gamma. Gamma MMP. And what I said, actually what you asked me a few minutes ago, is that steps of the MMP preserves non-decriticality. Okay, so this in particular implies that the original foliation was non-decritical. Okay, it's not possible to prove it directly from, I mean, at least I have no idea how to prove it directly from Y to X, because we have no idea what we extracted in order to get a minimum model. But if one is careful, you can divide this into steps, which are elementary, and these steps is very easy to check that the non-decriticality is preserved. So that's why the theorem follows. Okay. Now I would like to talk about another case of abundance, which is the opposite of what we talked before. As I said, abundance is false in general, and there are plenty of counterexamples, but there are two cases where it's true, at least as far as we know. One is the base point free theorem, and the second case is this one. Okay, so let's suppose that X, so we need to assume two factoriality for technical reason, but I don't think this is a problem. And F, as usual, F is a co-rank 2 foliation, so F is a survey. In other words, I'm going to assume that F delta is it's a low canonical. What am I going to assume? It's low canonical, sorry. But we don't need to assume non-decriticality, because non-decriticality will come for free. Well, I will show how non-decriticality will come. Assume that KF plus delta is numerically equivalent to 0. This means that if you multiply by any curve, then this is 0. Then it is, so in particular it's NF, because NF means greater or equal to 0 for any curve. Then it's semi-ample. What does it mean to be semi-ample in this particular case? There exists positive integer m such that m kf plus delta is equivalent to 0. Okay, so this in particular implies that kf plus delta is semi-ample. I should say that a special case of this conjecture was proven by Lorey, Pereira, and Tozay. Proved a special case. A conjecture, this in full generality. Although I don't think it's written down anywhere, but we heard from them this conjecture. Okay, so I'm not going to prove it because the proof is very technical, but I'm going to say the first main ingredient, which is one application of minimum of the program. So, sorry, this was the second application. And the third application, and again, this looks very familiar for whoever saw some variation geometry, some minimum of the program, but it could be quite technical if you've never seen this kind of stuff. So it's existence of FDLT modifications. This was one of the main results of BSHM somehow. Namely, if you have a pair, you can make it DLT. One of the main applications of BSHM. So how does it work? Let's suppose that F delta is a log canonical. Actually, we need even less, but let me prove it for log canonical. Let me show it for log canonical. Foliated pair. As usual, I'm assuming threefold rank 2. Then there exists I, which is a partial resolution. It's like a minimal resolution for surfaces from y to x, such that kfy, where as usual fy is the foliation induced on y, plus some gamma, it's equal to P star of kf plus delta, where gamma as usual is equal to the strict transform delta plus the sum of all the exceptional divisors of phi with coefficient 1, of pi, sorry, with coefficient 1. You take every single divisor with coefficient 1, and you have this formula. Of course, if I stop here, it's not very interesting. The pair Fy gamma is FDLT. Why is this nice? Because you see, if you take a random log resolution, most likely you're going to have coefficients here, which are positive or negative depending on the discrepancy. On the other hand, this theorem tells us that you can extract only divisors with which are log canonical places. In other words, or log discrepancy equal to epsilon ei. Okay, so it's a bit technical, but the reason why it's useful, because 2, it's a consequence of 3. Why? Because you see, here you start from log canonical, and kf plus delta equal to 0. But by applying this theorem, you can find kf right plus gamma, which is the pullback of something, and automatically this is FDLT. And of course, if this is numerically equivalent to 0, this is also numerically equivalent to 0. Okay? So, and also, if you're able to show that kf plus gamma satisfy this property, then automatically kf plus delta satisfy this property. In other words, this is semi-ample if and only if this is semi-ample. Okay? So the reason why it's much better log resolution is because you don't get coefficient with, you don't get terms with negative coefficients or anything like that. All right, so let me say just that 3 is the first step in the proof of 2. But 2, it's actually much more technical than what we expected, so I'm not going to talk about the proof of 2. Okay, one more, the last application, and then I'll talk a bit about the proof, is the canonical bundle formula. Which again is exactly the same as in the standard minimum of the program. So let's suppose that, as usual, F is as before, and F delta is log canonical. And let's suppose that F, small f, it's a fibration such that all the fibers of F are tangent to the foliation. Okay, so what I want, I need one more assumption. I want to assume that Kf plus delta is trivial with respect to this fibration. So let's assume Kf plus delta is 0 with respect to Qf. What does it mean? It means that for any F general fiber, actually for any fiber, sorry, there exists an M such that M Kf plus delta restricted to F is 0. Okay, so this Q is for this M, and this F is for this F. Okay, then what we can show is that, and this is again, you can have the same theorem if you replace Kf by Kx in Brownian geometry. F, it's induced by a foliation Y. And Kf plus delta is equal to the pullback of Kg plus gamma, where the pair G gamma is also log canonical. Okay, so this is somehow a way to say that if you're in the case where it's not Brownian anymore, this is equivalent, and somehow they appear very often more in fiber space, but you have a map into something which is lower dimensional, then assume, of course, that the foliation satisfies this property here, is trivial with respect of the fiber, then the foliation comes from below, and being log canonical is preserved. This is not, a surprising result. It follows actually from the canonical bundle formula in Brownian geometry, but still, it's nice. It's a nice tool to prove. For instance, we use it to prove the base point free theorem in some cases. Okay, in the remaining few minutes, I would like to talk about some of the technical tools we use to prove existence of fluids. Which of course is the main ingredient of our result. Sorry. Okay, so remember the setup was always the same. F delta is a foliated pair, which is F DLT. And we had a curve C such that kf plus delta times C is negative. And C span array, which is an extreme array. So something like this. Okay, so what we want to show is that C can be contracted, and also that it can be flipped. And also the locus of R, it's one-dimensional. In other words, this curve C does not move. There could be more than one C, but this curve C does not move. And actually, for simplicity, I'm going to assume there is only one such C. This is surely not a problem. So, for simplicity, we assume that the locus of R, it's only one curve C. So we have something like this. So somehow we want to contract C to a point, and then we want to flip it. Okay, so what is the idea? So we want to show, so the hope, the dream, or whatever, is to find some delta tilde divisor, of course effective, such that kx, and here I really want kx, plus delta tilde times c is negative. And also x comma delta tilde is log canonical. If I can do that, then I'm done. Why? Because I can use standard MMP. You know that flip exists, the flipping contraction exists, and the flip exists. Okay? But the question is, how do we find such a delta tilde? Okay, so if this curve C is not contained in a single locus of F, this is quite a straightforward result. So the most important case, the most difficult case is when C is contained in the single locus of F. Okay, so I'm going to talk about this case a little bit. Okay, again, my goal is to find such a delta tilde. Now, let's suppose, yesterday, by the result of Spicer, we say that there exists a separatrix, which is analytic and contains C. Okay? But somehow this is not enough. It's not true that Kx plus S, first of all, we have the problem that it's analytic, but this is not a real problem. But the main problem is that it's not true, I mean, by doing calculation, it's not true that Kx plus S times C is negative. Okay? So, under this assumption, by the study of surface singularities, and I will explain why, it's possible to show that there are two such separatrix. which are contained C. Okay, why is this a surface calculation? Well, simply because you have a curve. You cut through the general hyperplane, which will meet C in some points. Everything's analytic, so you can assume it's only one point. And you study the foliation singularity of the surface. I mean, on the surface, not on the... Then by the classification, it's possible to show that. By the classification, so by taking hyperplane, so this is the picture. We have our curve C. We have our surface H. And we study what happens at this point for the singularity. And it's possible to show that there are two separatrices, which of course are curves. Okay, so these two surfaces, these two curves induce two surfaces on the whole threefold. Okay, by doing for every point such a picture. Okay, it's a bad picture, but never mind. So the good news is that this is very easy to check. Kf plus S1 plus S2 times C is negative. Kx plus S1 plus S2 times C is negative. But why is this not good enough? I mean, why I cannot flip it? Well, the reason is because the bad news is that one of the two separatrices only exists in a formal neighborhood of C. Okay, so now actually there is also another good news. Sorry, I should have said before. X, S1 plus S2, it's also log canonical. But here I'm cheating big time because everything I'm doing, it's going to be in a formal neighborhood of C. So I should put hat everywhere. Okay? So why is this a terrible news? Because although there is some kind of MMP for analytic varieties, but there is no, I mean, we are very, very far away from proving a minimal program for formal schemes. Even Kodara vanishing is false for formal schemes. So none of the tools that work in bilateral geometry work in formal schemes, pretty much. So we cannot run MMP on X hat. Okay, so we need to do something else. Well, let me just say the conclusion of the story. I guess I don't want to be too technical, so I'm just going to say how we avoid this problem. So first of all, on a formal scheme, we can assume that, so X hat is the formal neighborhood of C. Maps to some affine variety, defined by some completion of some ring, in such a way that this is a birational, and the exceptional locus is exactly C. Okay, this is the easy part. Okay, in this setup, we can assume, we can show, using Artin plus Alkix, and I'm not going to talk about this because it's very technical, approximation theorem. One can show that there exists a sequence of divisor, SIM on X, such that SIM coincide with SI in the nth neighborhood of C. What is the nth neighborhood of C? So it's the neighborhood defined by the nth power of the ideal shift defining C. Okay? So we have an infinite sequence of surfaces which approximate both S1 and S2. So now, with a bit of work, one can show that this is quite straightforward. If M is sufficiently large, then, sorry, this is not straightforward. This next one is straightforward. This is also log canonical. What is straightforward is the following step. Kx plus S1m plus S2m times C, it's also negative. This is obvious. Why? Because to measure intersection, you just need to work on the second neighborhood. Okay, so you just want to take m bigger or equal than 2. Okay, so this is really obvious. This one requires a bit of work. Okay, but then we can really apply. Now we can really found delta. This is the delta tilde that I was talking about at the beginning. Okay, so we can apply Kx plus delta tilde MNP. So in particular, the flipping contraction exists and the flip exists. Okay, I'm a bit early, but nevertheless, I stop here. Thank you very much for your attention.